Hello guys and welcome to the Procedural Microchip tutorial series part 5. Today we have to make a variable grid of chip tiles, or an array you would say, and size it so that it fits into the cutout that we made last time. I'll be using a lot of vector math in this part, but don't worry, it's nothing complicated, it's just packing two operations at once into a single node, so don't be scared of it. Anyway, there's really not much to introduce here, so you know what, I'll just say it in the video. Well, guess what? Here we go. So today we will start a little bit unusual outside of Blender. Our main task is to do these chip tiles. So first of all, we will have to determine the size of each individual tile based on the available space that we have inside the window. We will have to make points on which we will distribute this tile. So we will do it by creating line on the x-axis and then distributing this line on another mesh line on the y-axis. So that will be our main task for today. So it will look something like this, and on each point of the line on the X, we will distribute the chip tiles. We have to do some calculations in order to find out parameters. So we will need the dimension of the tile and the length of the line that on which we will put the tiles on. So the length goes from the center of the farthermost tiles. Well, first thing to do is to determine the number of the spaces. That's n-1. So if we have 3 tiles, there will be 2 spaces, 2 tiles, single space. Then the sum of the length of the spaces that they take in the total width, it's the number of the spaces multiplied by its width. Then total width of the tiles will be the total width, that's x, minus the sum of all the spaces. Next parameter to calculate is the width of the single tile, and that's the total width of tiles divided by the number of tiles. And final thing is the distance between the centers of the span of the mesh line, and that's the total width minus a single tile. How is that? We go from center to the end, and that's 1/2 of the tile. The other half of the tile is on the other side. So in total, that's 1/2. The other half, that's a total 1 tile width, which we are subtracting from the total width. So these are the formulas that we have to take to Blender to calculate the parameters that we will need. Back in Blender in geometry nodes, I will probe the window, which we last used or manipulated the geometry of the scale elements here, and I will probe it with a bounding box. So the bounding box node will give me 2 vector outputs, except for the geometry, which is just a simple box wrapped around the original geometry. So if you put it there, it's the size of the window. Well, we can get rid of that for the moment. And what I will do is use the vectors of minimum and maximum and subtract the minimum from maximum to get the actual dimensions of the box. So if I use the vector math on this, vector math subtract, vector math subtract, okay? And subtract the minimum from the maximum. This will give me 3 coordinates, x, y, z, with the dimensions on each axis. Okay, before we close the side panel, let's actually add here the group input, and we will have to introduce some new inputs. Well, first one will be type integer, so let's just duplicate this one and move it all the way down to bottom. And this will be chip rows. Default will be 2, minimum will be 1, maximum can stay, let's say, at 20. Now let's add another one, chip columns. Again, default will be 2, minimum 1, maximum 20. Now one more, this time it will be type float, subtype distance. Default value will be 0.1 millimeter, minimum I think we can start at 0, and maximum we can leave it like that. We'll see what it does, we can adjust that later. Well, let's not forget also to enter the values here, chip columns 2, chip rows, chip columns, and I think I have to rename that, as this is the space between tiles, Okay, or tile spacing. That's better name, I think. Okay, tile spacing. Okay, that one will have to be 0.1 millimeters. Now, let's add yet another one. This time it will be type boolean. The name of it will be automatic rows override. So, I will do it in such way that when we are calculating the size of the window on the y-axis in steps according to the pin counts, I will use that value to automatically generate the rows of the chips. But in case you want to override that, enter your own number, you can do it by using this switch and actually enter the number manually here. So let's start doing that. First of all, I will add here I will again divide the pin count with min pin count and truncate this value. That's the calculation that we did last time for the size of the window, and then I will pass it through a switch node to the false value. So if the automatic rows override is false, then or it's not enabled, then it will output the automatic value. Otherwise, it will give us the value of the chip rows. Let's not forget also to plug in the condition, and we can go farther. Well, now I will combine these two values into a vector. So let's use a combine xyz. And what I will do is I will use almost exclusively vector math to do all the calculations both at once. If I would do it with the classic math nodes, I would have to use double the nodes in comparison if I use the vector math. Let's hide the side panel, and actually I switched the outputs. The columns are on the x-axis, so it's first column, second column, third column, and the rows are on the y-axis, so it's first row, second row, third row. So let's just switch the inputs to the combine xyz node and to fix that. For the z-axis, we can actually keep it at 0, but we will be dividing by this value, so let's change it to 1. Later on, I will fix the z value with another vector math operation. It really doesn't matter, but I just don't want to divide by 0. Blender, I think, will handle it, but it's not necessary to do that. Well, now, first thing that was in our equations was to subtract 1 from the n number, which is basically the rows and columns. So I will use a vector math subtract. So vector math subtract. Okay, and subtract vector of 1 for the x-axis and also 1 for the z-axis. Now, next thing we have to do is to multiply this value by a scalar number, so by the spaces actually. So let's add here another vector math node. This time I will use a scale, which what it does is multiplies all the components equally with a scalar value. So let's do it like that. This is our tile spacing, and that's multiplication of all the spaces in the grid, let's say, with the width of the space between tiles. Then what I have to do is subtract these from the value of the width and the height, or width and length, let's say. So let's subtract that, and finally I will be dividing it by this vector. So that should be the dimension of our cube. So let's actually plug it into the size socket of a cube and see the cube in our viewer. Let's see what we have. Well, that should be it. Let's test it out. Well, we have to enable the rows. Yeah, so it's scaling according to the rows and columns. Yeah, that seems to be working okay. Well, I said that I will fix the z vector for the cube later on. So what I will do is use another math node, multiply the x and y axis with 1. That will not make any change to that vector, and the z axis or z component with 0, that will zero it out here. Then I will use another math node, now set it to add, and for the x-axis I will add 0, the same for the y-axis, while for the z-axis I will add a value of 0.1 millimeter, and that will set the size of the cube here. Now let's make the points on which the instances of the tile will be placed. So I will use a mesh line for that. Let's add here that node. And first one will be the columns on the x-axis, so first, second, and third. So let's plug the chip columns to the count input of the mesh line, change the mode to endpoints, and the end location will be actually the size of the line, which is the size of this bounding box subtracted, and I will subtract from that the size of the tile. Well, so let's add here a vector math and vector math subtract. Okay, and subtract from it the dimension of the cube of the tile on x and y axis. To enter it into the end location, I need just the x component, so I will use a vector math multiply and multiply only the x component by 1, the other ones will be zeroed out. Okay, let's plug it actually into the viewer and see what we have here. Okay, we need to center it on the axis. Well, we could figure it from the size of it and move it by 1/2, but I will use a different approach. I will use an attribute statistic, which can output us a mean, which is a geometric mean of the position of all the points, or I will make it a position. So first of all, I will change the type to vector, and the attribute I want the statistic of is a position. So I will get a mean of position of each point or vertex on the mesh, and if they are distributed equally, we should always have the mean in the center. So what I will do is actually transform the mesh line with the mean. So if I plug it into the translation, I will probably get it moved on the wrong side of the axis. So what I need to do is use a vector math again, and multiply this vector by -1 on the x-axis actually, and not add but multiply. Okay, and that positioned it correctly. Now let's duplicate actually the entire setup here and do the same thing for the y-axis. So let's make a little bit of a space here. Also, I will add here a join geometry node and plug both the lines here into the output so we can actually see them. Well, we don't have yet plugged the dimension of that line, so let's copy the multiply node, plug in the result of the subtraction into the vector, and this time I will zero out the x-axis and use only the y-axis. Now use that for the end location. So that's set it on the y-axis, and now I will just use the switch output for the rows. So let's plug it to the count. And again, what I need to do here is to actually multiply the vector of the mean with -1 on the y-axis. And that centered it perfectly. So even if I have, let's say, the rows set to 5, it will always stay in the middle. Now let's just use the instance on points node, and the line on the y-axis will be the source of points, while the line on the x-axis will be the instance. So let's plug it into the viewer, and that's what it does. So if I decrease the rows, the columns, it will adapt to that. I think I can get rid of the join geometry node here and duplicate the instance on points. Use the previous instances as source of points and the cube as an instance. And now let's see what we have. And I think it's exactly what we were after. So if I change the rows or the columns that should react properly. And I deleted the joint geometry, but let's add it back and verify that we are within that bounding box that we took the dimensions from. So let's plug it here, and it seems that it's exactly inside of that space. Okay, let's turn it back to the rendered view or preview. And what it actually does is it's taking up all the space of the bounding box or of the window, and I think I need to decrease it a little bit. So let's plug the result actually into the joint geometry node of the complete microchip. Let's find that. It's all the way down here. And we can disable the joint geometry in the viewer, and what we'll have to do is move it somewhere upwards. I will put here the temporary transform geometry node and just move it with 1 millimeter up. Actually, it's 0.1 millimeter, so let's do it like that. And this is not what we want. We want it to be the chip tiles to be a little bit smaller than the window itself. So what I will do is I will add another vector math node here, set it to subtract, and replug the nodes here or the lines here. And what I will do is subtract from the size of the bounding box constant value, and the value will be 1.25 millimeters, which will decrease the size of the chip tiles, and that should be what we need. So the 1.25 millimeters should be enough to encompass even if we change the radius to something to this complete circular window, and it should really accommodate that. Let's actually enable the automatic rows, change it for example to 10, and we have it nicely inside. Maybe change it to 1.3 millimeters actually on both the axes to be really sure that it stays inside 1.4 millimeters. Okay, I will do it like that. Well, let's just return the fillet to something normal so that we don't have the circular window, and let's enlarge the chip a little bit. And the next thing I will do is to add a base plate below the chip tiles. So again, I will add here a cube, which size I will again determine from the bounding box. So I will use the full size of the bounding box. So let's add here a again, and I will be subtracting from that vector some value. Well, I will drag out the size of the vector that I am using to shrink the bounding box for the tiles, and I will put it into a vector. And what I will do is multiply this by actually scale that. So scale that by 0.5, and I will subtract this value from the bounding box. So this one will determine the size of the base plate. Well, let's add here a viewer so we can actually see it. And also what I will do is again use the zeroing out of the z-axis and adding there the constant value. So let's change that. We can keep it at 0.1 millimeters. Now let's just join the base plate with the tiles. And first of all, I think what I will do is add a realize instances node here on the instances of the chip tiles. That's because first of all, the bevel is not being applied to the instances, and then also when we will make the material for the chips, I think it looks better when the instances are realized. Otherwise, all the instances have the same layout of the random noise or brick texture, for example, what we will use. Okay, let's not get rid of the viewer, and let's add here a join geometry node. So that, and plug the base plate here, and actually, well, let's use this for the viewer, And what I will do is I will change the translation of the tiles for half of the height of the chips. That will make it sitting half inside of the base plate and half outside, and I don't mind that. I will keep it like that. Then what we will have to do is translate the entire geometry, and to do that I will actually probe the pocket of the... Let's get rid of the viewer. I will probe the shape of the cutout, or the cutout shape, cutout object for the window for the lowest point. So I will again use the attribute statistic for the transformed geometry. So let's add here a attribute statistic. I will be using vector mode. The attribute will be position. Okay. And from that I will use minimum. That's the lowest point of the object. So also I have to probe the joint geometry for the lowest point. So again I use the attribute statistic here. Again use vector, attribute is position. So let's move it somewhere else. And actually we can get rid of the viewer now and add here a transform node, transform geometry node, plug it on the line of the joint geometry that's coming back to the joint geometry of the entire object. And as the vector, we will use a vector math again. So let's add here a vector math, change it to subtraction, and I will be subtracting the minimum value of the position from the minimum value of the cutout object. Well, enter it into translation, and that should position it perfectly. It did, except it has positioned it also on the x and y axis, which is not what we want. So let's just simply eliminate the translation on the other two axes, on x and y, with vector math set to multiply, and only z axis will be used in that. And that's our base plate with the chip tiles placed inside the window. What I think I will have to do is enlarge the base plate just a little bit. So I will scale it with some factor like 0.75, I think. No, it's subtraction, so 0.25, and that should give me enough space for the contact fields of the wire leads that I will add later on. The last thing I will do here in the geometry node layout is to assign material for the base plate and for the cube. So I think I will duplicate the group input and place it somewhere here, and then add a set material node. So first thing I will do is plug it on the base plate. That one I will have it to use the same material as pins, so metallic material. And for the chip tiles I will add a new material, so I will plug it into an empty socket and actually open the group input window here and change it to material CPU and move it actually to the materials. And what I think I will do also is I'll move all the material downwards on the inputs. I think it's more logical to assign the materials as the last thing, I guess. So let's move them downwards. Okay, and also the CPU, and move it down to the bottom. Okay, I don't know if it's better or not. Well, maybe that screwed up the rest of the layout, but I will keep it like that. Okay, now again, I will select everything that I have here, except for you and you. Then I will move it upwards, and again in the node wrangler, click frame selected, and name this as the chip tiles baseplate. Chip tiles baseplate. And with the 20 minutes and something mark gone, that's where we will wrap it for today. So thank you for watching, and don't be disappointed that we didn't finish the CPU shader. It will be coming out as a standalone video sooner than you think. So make sure you hit that subscribe button and don't miss any of the upcoming parts. See you at the next video.